Okay, so again, we want to avoid using in 3.2, avoiding using the formulas that come up in this lesson if you can. Sometimes you'll need them, but you don't often need them. Okay. So first of all, we need to define dependent events. A and B are dependent if the probability of one depends on the other's occurrence. Okay, so sometimes the second you know one thing's occurred, that changes the probability of the other. So, I can figure out what the probability of a let's say a college student getting in a car accident is, but I know that the probability changes if I'm told that the student is a male. Nothing personal, guys. I'm a male too, and I had to pay higher rates when I was in college for insurance. And the reason why is just because males are higher risk. We get in more car accidents. So the probability of getting in an accident depends on whether you're male or female. And so those are called dependent events. That is, being in an accident is dependent on your gender. Okay. So they influence each other. Okay. Now, there's a special type of probability called a conditional probability. This depends on a condition. Okay, so P of A with a vertical line and a B is the probability of A given that B has occurred. That's a condition. So in that, we assume that B has occurred. Okay. So that only matters if A and B are dependent. If B has occurred, yeah. So if B has occurred, then that's going to affect the probability of A, which makes the events dependent. So if the events are independent, it's easier. The probability of A and B is what I showed you before. It's just the probability of A times the probability of B. Easy. If the events are dependent, then you have to be more careful. The probability of A and B is the probability of A times the probability of B, but it's the same thing so far. The only thing is that A and B are a package deal. When you say probability of A and B, you're assuming both of them are occurring. So when you compute, if the events are dependent, then the probability of B depends on whether A has occurred or not. So because we're asking the probability that they both occur, you have to assume that A will occur when you do the probability of B. Okay, so that's the probability of B given A here. Okay, any questions about that? Okay, so it says toss two fair coins. What's the probability that they're both are heads? Okay, so A, let's say first is heads. And then B will be the second is heads. Are they independent or dependent? Does the probability of B depend on whether A happened or not?
No.
No. So yeah, these are independent events. Let's go ahead and say that these are independent. Okay, so if I do the probability that they're both heads, that's A and B. This is just the probability of A times the probability of B. And then you have to say, well, what's the probability of A? Well, there's one way to get heads with two outcomes. So it's 1 out of 2, 1/2 for A, and same for B, 1 out of 2. One way to get heads out of 2 outcomes. And of course, 1/2 times 1/2 is 1/4. So you can write that, you can just leave it as 1/4 or say it's 0.25. We do have a rounding rule, but that's not rounded. So I don't fuss with rounding rules when you're not rounding. Okay, and if you want, you can say that's 25%. Okay, are there any questions? Okay, now this one, you guys okay?
Yes.
Yeah, and you can just do this over and over again. You drop 2 coins, and in the long run, you'll get 25% of them that come up with 2 heads. You have to do it for a long time. You can't just do it 10 times. But if you do it 100 times, you'll see about 25%, not exactly, but approximately 25% of the drops will have 2 heads. If you do it 1,000 times, it'll be even better. Okay, so now here, this is really similar, but you're picking cards from a deck and you're not replacing the first card when you draw the second. Okay, so here, this is really similar. I'm going to say A equals, we want both hearts. So A equals first card is a heart. B is second card is a heart. Okay, independent or dependent?
Dependent.
How come?
Um, I don't know. It's too hard.
Oh no. You sounded so confident.
Yeah.
Is it
That-
dependent? Because it
that-
has there's only 4 possibilities for hearts.
well, there's 13.
Oh, 13, I mean, yeah.
Yeah, well, what does that mean? So you're not replacing the card. What does that mean on the second card?
Less chance for the second card to be a heart.
Yeah, because there's fewer hearts now. So, but if it's not a heart, if the first card's not a heart, then the probability goes back up again. So the second card being a heart depends on whether how many hearts are in the deck. And that depends on what happened with the first draw. So is there 12 hearts or are there 13 hearts in the deck? You follow me? These are dependent events. Okay, so these are dependent. Since the second event, let's say since probability of B depends on whether A happened. Okay, so here I'll do probability of A and B. This should be the probability of A times the probability of B given A. Okay, I'm going to make a little more space. Okay, so, again, there's 13 hearts. and you're drawing 2 out of 52, and you're not replacing the first card when you draw the second. So what's the probability of A? First card is a heart. Again, there's 13 hearts.
1 out of 13.
So you want to take the number of hearts and divide by the total number of outcomes. So how many hearts are there?
13
Good. Out of how many outcomes?
of 50 something.
Yeah, 52 cards altogether. And then next, we want to do the probability of B given A. Now you have to put your mindset in. All right, the first card is a heart. It has been set aside. So now how many hearts are left?
12,
Out of how many cards?
51.
Good. Perfect. So 13 out of 52 reduces to a fourth. 3 actually goes into 51 and a 12. So you could say this is 4 out of 17. That's how 12 out of 51 reduces. And of course, that's 1/17. I'll go ahead and do a rounding just to practice it. So if you do 1 divided by 17, you get 0.0588. So this is approximately 0.0588. Just as a reminder, you're supposed to keep 3 significant figures. If you're going to round. Okay, a significant figure is not the lead. The only thing you have to remember about significant figures is that the leading zeros aren't significant. So if you have a leading 0, you've got to carry another digit. Okay, it's 4 digits, but there's only 3 significant ones. Okay, any questions about that? All right. Now, so that was all multiplication rule, pretty straightforward. And then the addition rule depends on whether events can be exclude each other or not. So mutually exclusive events, A and B are mutually exclusive. If they can't both happen. Okay, one will always exclude the other. Okay, and I guess I should say in one experiment or trial, maybe is a better word. Oops, I don't know how to spell trial. Okay, so they are mutually exclusive. So if you pick one card, okay, is getting a heart and a spade, are those mutually exclusive? If you're picking one card, a heart and a spade, let me show the picture again.
No.
Can they both happen with one card, a heart and a spade?
Yeah.
Yeah, well, no, I mean, there's no card that's a spade and a heart. These are different groups altogether without overlap. So the second you know it's a spade, again, it's one card. The second you know it's a spade, that excludes it being a heart. The second you know it's a heart, that excludes it being a spade. So they mutually exclude one another. They cannot both happen. So the answer is that those are mutually exclusive. Okay, so for events that are not mutually exclusive, the probability of A or B with the addition rule is just the probability of A plus the probability of B. Okay, just like that, super easy. And we saw that in 3.1 with an example we did. When events are not mutually exclusive, it's more complicated. So you have to do the probability of A or B is the same probability of A plus the probability of B. But now, if these are not mutual, sorry, if these events, oh, did I get this mixed up? Not mutually exclusive. Okay, so I've got this mixed up. This one says not mutually exclusive here, which means they can both happen, like a heart and a queen together can both happen. And if it's possible for both events to happen, what will happen here is you'll double count on the first one. So you have to subtract out the double count where A and B both happen. Okay, so I apologize for that little mistake. That was the one we did in 3.1. Okay, and if the events are mutually exclusive, then probability of A or B, you just add up the probabilities. Okay. This one looks like a little bit more complicated here. So it says toss 2 unbiased coins. That means it's a 50-50 coin, 50% chance of heads, 50% chance of tails, not 40, 60 or anything like that. So what's the probability that one is heads? Okay, so probability that one is heads, let's do H for heads and T for tails. Okay, so probability of one heads, you should be explicit. This is probability of getting a head and a tail, or a tail and a head. Those are two different tosses, because if you think about it, let's say you get a head and a tail, take those two coins and turn them over, and you've got another head and a tail, or a tail and a head, I guess. The point is, it's a completely different toss. You flip the coins, you get it again. So we have to count it twice, because things that can occur in two ways are twice as probable. You've got to count it twice. Okay, now, when you see or, these events are mutually exclusive. They can't both happen. Okay, a head and a tail, or a tail and a head. It's one of the two, but it's not both. Okay, so they mutually exclude each other, and or means add. So you would change this to probability of heads and tails plus the probability of tails and heads. Okay, and then and means multiply. These events are independent because one coin is not going to influence the other. Okay, so and means multiply, so the probability of heads times the probability of tails plus the probability of tails times the probability of heads. Okay, and of course, they're all a half, because getting heads is 1 out of 2, right? And tails is 1 out of 2 as well. So you're just doing a half times a half, which is a fourth, plus a half times a half, which is a fourth, and a fourth plus a fourth is a half, which is 50%. So there's a 50%, if you drop 2 coins, there's a 50% chance that one's a head and one's a tail. And that just totally makes sense. But that was a pretty hard way to get there. But at least I've proven it, I guess, if you want to call that a proof. Any questions about that one? We're not going to do super hard probabilities on an exam. This is just sort of getting your head wrapped around some ideas But most of the probabilities we really need to do are with the bell curve. So this is just, again, this is just an intro to probability. And we'll forget a lot of these. I don't know if we want to forget them, but we won't use them directly. We'll use them indirectly. Okay, complement. The word complement here has an E instead of an I. A compliment with an I is a nice thing you say about someone. And a complement with an E is to complete something. So the complement of an event is just everything else, everything that's not that event. So we just say if A is an event, any event, oops, hang on. A complement so you read that A complements, but we just write it as an A bar. Okay, so A complement is the event not A. So it's everything that isn't A, which completes A, which is to complement A.
So complement means to complete something.
Complement with, yeah, so it's like this complements your wardrobe. That means it completes your wardrobe.
Okay.
It's everything that's not, that which completes is the complement. But it's just everything that, you know, that isn't A is what you need to complete it. Okay, so so the rule of complements, just want to make a note. If I say A or A complement is a certainty, what I'm saying is either something, it doesn't matter what it is, either that event will happen or not. That's a certainty. Okay, so what I mean is the probability of A or A complement is 100%. One, the number is 100%. One of those must happen. So the rule of complement says, okay, we can use the addition rule. If one of them must happen, that means the probability of A plus the probability of A complement has to be 1. But this is totally common sense, you guys. You do it all the time. So, you know, if I say there's a 30% chance of rain today, what's the chance it doesn't rain?
70.
Yeah, 70%. That's the rule of complements. They have to add up to 1, which is 100%. Okay, so more directly, yeah, go ahead.
So since they're supposed to add up to 1 and it's only for mutually exclusive kind of case, right? But like
Right.
if they are independent, can they like go above 100?
We don't do independent for the addition rule. You were right when you said mutually exclusive, and these are mutually exclusive because something can't happen and not happen. So they do exclude one another. Therefore, or changes to plus with the addition rule. No probability can go bigger than 1. So these will be exactly the complement of each other, which is to say they will exactly add up to 1. So probability of A plus probability of A complement is 1. What we really want to do here is say that the probability of A is 1 minus the probability of A complement. And I'll just say that you normally use this when a complement is easier than A. Okay. You'll see some I mean, this problem we did up above where what's the probability of getting one head when you toss two coins? That's actually sort of complicated. There was two different ways to do it, and I had to really break it down. Okay, now the complement of that was also complicated, so it wasn't worth using the rule of complements, but sometimes the complement is pretty easy. Let me do first a simple example. Like I said, if A is it will rain today, and let's say the probability of A, I think I said is 30%. Then a complement is it will not rain today. And the probability of a complement is 1 minus the probability of A, which is 1 minus 0.30. And of course, that's 70%. I'm going to make a little more space there. Okay, so that's a super easy example. But just to kind of help you see that this rule of complements is absolutely common sense. But, you know, it's almost so common sense, there's no point in saying it, except for when you have this issue where the problem you're given is super complicated, and it's just easier to look at the opposite event. Okay, so that obviously I have an example of this here. So it says you've got a batch of fuses, okay, 15 amp fuses. All right, 10% of the batch is defective, which is a bummer. If 5 random fuses are selected with replacement, which means the probabilities won't change, you're going to keep putting them back. What's the probability that at least one is defective? All right, so let's break this down a little bit. Let's say D stands for defective. Okay, so what's the probability of D? Oops. It's a given, by the way.
10% of 15.
No, it's just 10%. The probabilities, remember, are percentages. So probability of D is just 0.10, which is 10%. Now you do have 15. See, this 15 right here is just the type of fuse it is. So the 15 won't come into play in this problem. I don't know why I put in 15 amp fuses, but I just did. Okay, so so the probability of a defective fuse is 10%. Okay, and then if I do D with a bar over it, remember the bar is the complement, and all you have to do is put not in front of the word defective. Okay, and the probability of D complement is 1 minus the probability of D. So I'll just say 1 minus 10%. Of course, 10% of them are defective, which means 90% of them aren't. Okay, that's obvious too. I didn't really need a rule of complements to determine that. We knew it already. Okay, now the more complicated bit is that you've picked 5 fuses and they're saying what's the probability that at least one is defective? That's sort of complicated. So A, I'm going to define to be the event at least one is defective. Now, if you think about what that means 1 or 2 or 3 or 4. You've got 5 fuses and at least one is defective. So it could be any number. At least one means no less than 1. So that's 1 or more. Okay, 1 through 5, you only get 5, so you can't have more than 5 defective. Now that's what I mean when I say if A is complicated. This thing can happen in a lot of ways. And every time I say or, that's an addition rule. You follow me? So there's a lot going on here and I just don't want to do it. So it would be easier to look at the complement. Okay, so what does it mean that not at least one is defective? How many would be defective then? Out of the 5 fuses.
0.
Yeah, it's not 1, 2, 3, 4, or 5. It has to be 0. They're all good fuses. So none are defective. And so what I'm getting at here is that's a lot simpler. Okay, none are defective just means 0. Okay. We're not going to do problems like this, but there are going to be many cases where we go, you know what, it's just easier to do the complement of this. And let's just do the opposite and then use the rule of complements. Okay. So for none to be defective, that's going to be, I think, just a simple multiplication rule. So let's do it this way. Probability of A is the question that they're asking us to compute. Okay. We don't want to do it because A is this 1, 2, 3, 4, or 5 defective fuses, super complicated. So it's easier to do just 1 minus the probability of a complement where none are defective. So for none to be defective, that means all 5 fuses are going to test not defective, which means the first one is going to be decomplement, not defective. And the second one, decomplement. There are 5 fuses and none of them are testing defective. Okay, so that's a lot of multiplications. You're picking the fuses with replacement. So these are all independent. And if you want, make a note, that's because we're picking with replacement. So every time you pick a fuse, it's just like when you picked the prior fuse because you put it back and then you did another random pick. Okay, so if they're independent, and just means multiply. Okay. So here you would just do 1 minus the probability of D complement times probability of D complement, and you just keep writing that out. So there's 5 of them. We just raise that to the 5th power. Okay, so this is 1 minus probability of D complement was 90%. So I'm going to write 0.90, and that has to be raised to the 5th power because you're doing it 5 times. Okay, and that's still complicated. You going through the back door with the rule of complements. It's still complicated, but it's a lot less complicated than doing the problem directly, where we just do all the possibilities 1, 2, 3, 4, 5 defective. That ends up being a huge task because each one of those is actually complicated as well. So this is the simplest you can make the problem. Okay, and I think I'll show you Desmos real quick, just because. So let me pop looking for Desmos. So forgive me. I guess I can just do a share of my desktop. That's fine. Having a little trouble. Okay, so you're looking at Desmos again here. I don't want any of this stuff, I don't think. So I'm just gonna get rid of all this garbage. Okay, so just so you can see it, there's a little toolbar. If you do 1 minus 0.9 or 90, if you like, then there's a little pop-up toolbar at the bottom here and an exponent right here, a to the b will give you a raised exponent there, and you want to raise it to the 5th power like that. Okay. So I think this is 0.4095, which we want to round. Okay, any questions? Okay, so what did I say? I forget. 4095 approximately. And if we were to do 3 significant figures, we would do 0.410. Now, just a note, the trailing zeros are significant. So you don't want to drop that 0, even though it doesn't add more value, it doesn't add value to the number. It tells you we know that digit is a 0, so I'm recording it, and now I have 3 significant digits. So maybe just a note here that says trailing zeros are significant.